So good morning, all the participants at different nodal centers and participants in the studio. Uh, Today we are going to start with the next part of this program. So we discussed all, I think in 2-3 sessions we covered optical fibers, uh, optical waveguiding through or light propagation through optical fiber, then transmission characteristics, and then yesterday we also covered fabrication and cabling process. And in the afternoon session, we also demonstrated some of the experiment through which uh, we, we can characterize the optical fiber, or different parameters can be measured. Now the other part of our OFC system, I mentioned in OFC system basically comprises of optical source, optical detector, and optical fiber. So regarding optical fiber, we have discussed in more in quite detail. But optical source and optical detector, they are equally important because your system will comprise of all these three components. But optical sources and detector, mostly they are at one location, or generally in the telephone exchange. So as a result, they are in a very controlled environment, so may not be affected much by the external factors. So but they are very important, because whatever you will launch from an optical source, that is your basic information. If your basic information is not optimized or not of high quality, naturally you cannot expect a good quality at the destination. So now for this session we have us, Professor J.K. Chhabra. Professor Chhabra worked at CSIO Chandigarh for around 30 years. So he retired as ex-scientist, as scientist G from CSIO Chandigarh in 2008. Then he joined as professor in the Department of Electronics and Communication Engineering at Jean Institute of Engineering and Technology, Jean in Haryana. Basically, he was in that college. He was looking at the R&D activities or project of the student in the area of electronics and communication, and specifically in the area of optical fiber communication. During this period, in between, he also joined as consultant professor at IIIT Allahabad, where he was instrumental in developing a fiber optic sensor for Department of Forest, in order to monitor or vigilance the wild animals in the forest areas. So they have installed a sensor near in, I think, in Madhya Pradesh. In Madhya Pradesh, with in collaboration with IIIT Allahabad. And then he is also a source person for most of my program, and very much experienced person, not only on the theoretical background, but practically he handled many projects at CSIO in development of optical fiber communication system and sensors specifically. So I'm thankful to Professor Chhabra for accepting my invitation. So today he will speak on optical sources and detectors for optical fiber communication. Then he will also engage another session on tomorrow and day after tomorrow on other topics. So I hope during this session he will try to cover basically the compatibility of optical sources with the optical fiber. Otherwise, it's very difficult to cover optical sourcing and detector in this a slot of 1 hour. But he will try to give the importance of optical sources, different performance characteristics, and compatibility with the optical fiber. So with these words, I request Professor Chhabra to start the session, please.
Good morning, everybody, even in the distant locations. And I welcome you to this session, to this beautiful communication lab. This is my first experience in this lab. The optical fiber communication, see, the father of this is supposed to be a cow. Of course, Narendra Singh Kapani was his associate, but somehow, he went into industry and Cow kept on to the R&D. So he's called father of fiber optic communication. And I understand you have already had a video. So Cow is supposed to be the father of fiber optics communication, and he was awarded with Nobel Prize. And you've also seen how he came to the conclusion that he showed it practically that how optical fiber can be used for communication. But at that time, what he was trying to show in his laboratory was just a few meters of optical fiber in which light could travel few meters only. That means it was such a lossy fiber, and the source he had was almost size of your window air conditioner. That was helium neon laser. But what he said at that time, that we will be able to communicate over long distance of miles together if we have an optical fiber which is 4 dB per kilometer loss. That is, you know, optical fiber available was, I think, 100 dB per kilometer at that time. So he said this, and immediately Corning took up the challenge. Now, Corning immediately developed, say within a year, they developed a 4 dB per kilometer multimode fiber. And other laboratories were also working on that. Probably cannot be transmitted over longer distance. And the first window, as you can see in this, first window, as we can see, is between 800 and 900 nanometers, which is near infrared. And the sources could be modified to get light in this region. Because what we had, the smallest source that we had at that time was LED. And LED, what LED was there? Red LED. Red LED is useless for fiber optics. It will not send light even few meters. So they said, let us modify the LED material in such a way that we are able to get between 800 and 900 nanometers. And immediately LED was modified to emit this light, as well as it was modified in such a way that it can launch light into optical fiber. Otherwise, the light that was being say launched by LEDs was like, you are filling a test tube from a tube well. So all the light is going waste. So you needed at least a tap to put under it a test tube. Let some light go, but it should not be like a tube well water coming into a test tube. So they immediately modified the optics of the LED, and with that they were able to launch now light of 800 to 900 nanometer, that is basically 850 or 910 into optical fiber, which could travel now 4 to 5 kilometers. At the same time, development was going on for 1300 nanometer, because you can see if the loss is 4 dB per kilometer in case of 800 to 900 meter devices, the first generation, it would be even less than 1 dB. So you can go 10 times or 20 times more with a light source having in this band very fast. They developed light sources in the 1310 nanometers also. And see the beauty of nature. Optical fiber has minimum dispersion at 1310. So dispersion was low, loss was low. So big effort by AT&T and Bell and other companies. They pushed it so that they could get sources in this region. Similarly, another God gift, I'll say, because had developed and that was lasers. So laser, which was helium neon or ruby or whatever, they said, let us think of a laser which is also compatible with fiber and let it be the size of LED. So a big effort for this, because in industry, one is for money and in the R&D labs, it is for Nobel Prize. Both, some people want money, some people want glory. So both combined, because if you get glory, if you get a Nobel Prize, your book sells like anything. So it is also business. So same thing happened here also. And they could develop sources which were lasers. These lasers were much more compatible with optical fiber, and today they have taken us to this stage where you have terabits of information being transmitted transatlantic or from US to Japan 24 hours, and it is in terabits. They are thinking of even higher petabits. NTT is developing systems which are petabits. So just like this, in a meeting way back in 90, we were with our director, and he was from IIT Kanpur, Professor K.R. Sarma. So he said, in one of the lectures in IIT, I asked, if I give you, because at that time it was kilobits, computers were kilobits. And he asked the students, if I give you gigabit transmission capability or speed, how long you will be happy? They once said, sir, for 1 microsecond we will be happy. After that we will want more. The greed. If I give you 1 crore, how long you will be happy, sir? For 1 day. But because I want 10 crores or 100 crores. You have one aircraft and you start thinking, our airport ho to tax nahi dena padega. So I should have my own airport. So that is the greed, but sometimes greed helps in development. And this is how the greed for bandwidth led us to better fibers, to better light sources, and to better electronics. So this is the main theme of what I wanted to say. Now let us see how it has progressed over a period of time. So types of optical fiber sources which are compatible with optical fibers, initially laser LEDs, and then, as I said, the lasers came in. The LEDs emit incoherent light through spontaneous emission. Two materials, when we have a PN junction, then when you give a forward bias to this, at the junction, because of the properties or because of the energy levels or because of the electronics, which we know PN junction, light is emitted at that particular junction. And depending upon what the two materials are, P and N doped, the color of the light depends on the material that you use. So you have a broad spectral light from this PN junction, and this PN junction, you have a broad spectral band light, and now we want this band gap. No, I mean to say the spectral bandwidth to be as narrow as possible. Supposing it is from 900 to 950, all the wavelengths will be there. I want only one or two. So this was another pursuit, and which led us to lasers. But because LED was there, basic technique to get light from a semiconductor material was there. Everything that was left was how to modify it and refine it. So LED was actually we say LED is useless now for a single mode fibers, because we cannot launch any light into single mode fiber with the help of LED. But it was the LED which gave us the idea that light can be had from a semiconductor material also, and this led us to the what we have today. And at the same time, as I said, due to synergy, we had lasers were already there, but we tried to miniaturize them into a semiconductor material. So we got semiconductor lasers also. So from LED, as I said, if I had used different materials, for example, I use aluminum, gallium, indium phosphide, then I will be get 6.1 to 0.68. That is something like close to red. You will get red light. Whereas if you have aluminum, gallium arsenide, then 0.8 to 0.9, which we wanted, and we got them very soon just by changing the material of the PN junctions. And then now Indian gallium arsenide, this could give us I'll say 1000 nanometers to 1300 nanometers. And then fiber is even better if we go to 1500 nanometers or to 1800. So there are light sources which can give you Indian gallium arsenic phosphide. It is like, we have the basic semiconductor material, we have P and N impurities, and similarly for light emitting also, these materials are there. Which one? Indium, arsenic, phosphorus, and they are able to give us even light and infrared region. So LED output characteristics, if we look at them, as you increase the voltage or as you increase the drive current, more and more light is emitted. That is, you get brighter light with this. And we have different diodes in which then at certain range, the intensity will not increase. That brightness will not increase, but it will come to a plateau. Diode 2 and diode 3. So these are current control devices. The light depends upon the current flowing through the junction. So if we can change the current somehow with a signal, then this, if we launch into optical fiber, we will be able to communicate. And faster we can modulate, the faster will be the bit rate. So this was the basic foundation of thinking that optical fiber communication is going to be successful. It will take over the other because optical fiber had those properties of EMI, RFI, interference cannot affect it. It can be in water for many days. Nothing will happen to it. It is lighter. The weight of 1 kilometer of optical fiber is only 14 grams, 1 tola. So lightweight cables will be possible, non-inflammable. All those properties were there. And this gave us an idea that if we modulate or if we change the light through variation in current, it will be possible. The same things held for laser diodes also. Once again, it's a current control devices. So they started developing very fast. LED has, I say again and again, LED has given us a foundation to get into optical fiber communication. But Kao wanted these and he got them. Actually, he gave a very good lecture on when he got Nobel Prize, because normally the Nobel laureates give a lecture. So he gave from sand to something, he said, I can give you that lecture, say website. Beautifully, he has explained how sand has been, from sand we have got optical fiber, and then how it is going to affect the world. Because he is giving his Nobel laureate lecture after something like 20-25 years. So when he looks back, he says, sand has made this possible. I, okay. So the types of LEDs that were available was red and all. But for optical fibers, you will hear always the terms edge emitting LEDs and surface emitting LEDs. I say it in very simple language. It is like having a burger or a submarine sub or some other kind of patty or something which has layers of materials arranged in such a way that you are able to get a specific wavelength of light as well as in a particular direction. Some will come in some, the light will come out of a sandwich like this. In others, it will come from. So edge emitting, surface emitting, these are different geometries of the sandwich or the how the materials have been deposited in layers, and light emitting area will be made like that. So edge emitting LEDs you will really hear, but basically for you as a user, whether it is edge emitting or whether it is surface emitting doesn't matter, as long as the light you are able to couple into optical fiber. They have their own efficiencies, advantages, and other things. So this is the LED for fiber optic communication, and there is a coupling lens also is can be incorporated in between, and this is possible. It is possible to use this for short links. This LED is compatible with only multi-mode fibers. It cannot launch light into single mode fiber. And the data rate could be 20 megabits Mbps. This was possible, but still for LANs and other applications within the building, within premises, multimode fiber and LEDs can be deployed. The cost is very less because both LED and multimode fiber together cost is very less. Maintenance is easy. So connectors are cheaper. So many places still use LANs and other inter-building or inter-campus networks using LEDs and multimode fibers. The surface emitting, as I said, it is type of a sandwich. That sandwich of various materials put in layers, and this where in region where the light is emitted. This is the region where light is emitted. And in order to say, if I give that analogy of tube well and test tube, what is done is we say we don't leave the test tube to you. We will put the optical fiber at the emitting area itself. We will see when the light is maximum into optical fiber with the help of emitter at the other end, and then we will freeze it. We freeze it and then we seal it. So now I give you a device with a pigtail. That is a device from which an optical fiber is also coming, and it is sealed to that. Now what you have to do is only connect this fiber to your spool or to your reel or to your fiber going away. That can be through two connectors, or it can be even fused. So it is much easier to align rather than trying alignment with one thing and another connector and things like that, because you will have to put LED into some receptacle. Centering of that should be equal to connector centering, and then every time that you move some misalignment can come. But so what we have now, a pigtailed optical fiber also put to the in front of the light source. So it makes life easier. Now, edge emitting, as I said, it's a different type of sandwich. sorry. Here the light is emitted from the side. But for us, when you see, it is just like any transistor with a glass window. We don't know whether it is edge emitting or whether it is surface. For us, it is a light source. But technology, how to improve the efficiency and how to maintain a very smaller, I'll say, spectral width, that is important for these technologies. Then what is most important in case of LED specifications is how much is the optical power, optical output power in that. It can be something like milliwatts because the current is 100 milliamperes maximum. So we get few milliwatts, but only from this few milliwatts, say 2 or 3 milliwatts, we are able to launch even in multimode fiber only 20 microwatts. So if the light being emitted by the LED is less, you will be able to launch only lesser light. So normally we are interested how much is the optical output power of the LED. Then what is the output spectrum? In which bandwidth or in which particular wavelengths are being emitted? It has a spectral width of about 50 nanometers. Whereas that may have a spectral width of 1 nanometer. We'll see tomorrow. Even less than 1 nanometer spectral width. That's so pure light you can get from laser. Then light coupling into fiber. As I said, even if you are getting 3 milliwatts, you are able to couple only 10 to 20 microwatts into this. So this will also be given in the specification that how much you will be able to couple into a multimode fiber. And remember, the multimode fiber is either core is either 50 microns or 62.5 microns or 80 microns at the most. So in a 50 micron single mode fiber, you will be able to couple 10 to 20 microns. But these are the important specification plus modulation bandwidth. How variation of current will respond to the signal. So that is also important. So we have 4 important parameters in case of LED: optical output power, output spectrum, light coupling into fiber, and modulation band. These are universal type of specifications because they will be as good or important for laser diodes also. How much laser diode is emitting, how much we are able to couple, and at what speed we can modulate. These are important for any light source for our communication purpose. Then they have been developing, on the other side also. They said, we will not give you much trouble. In the LED itself, we will put a small lens, we'll put a small mirror, or we will put a covering so that the light we are able to focus onto your fiber from the LED LED itself. So you will have to do less focusing and all this from outside. The device itself has inbuilt lens or other optical optical elements to give you a focused light. Then came laser.
It's a crystal, very much like gallium arsenide, tiny crystal with mirrors front and back, polished and cleaved, so there's a largely reflecting surface on both faces. And you pass a current through the diode that populates the space inside the junction with electrons and holes. And these recombine and produce light, which is bounced back and forth through between the mirrors, and that is inspires more electrons and holes to recombine and singles out, instead of a broad beam of spectrum of light, it concentrates at a single frequency, and all the light comes out in a very intense collimated beam.
Okay, thank you very much. So you can see that this laser diode, which was a breakthrough, came up, and the things became then easier for fiber optic communication. And 50 years of laser, or 50 years of light, this laser were, I think, in 61, so you can 2011, and the professor was alive, and he was there in those celebrations. Then just after this laser came, the US government gave a contract to RCA, Radio Corporation of America. They were actually making radios, and they were making records just like HMV. So they gave contract of developing lasers, and see, they had a gallium arsenide laser diode of the size of just like transistors. Yes, so they had this kind of laser, and they advertised like this, that our light beam can travel through eye of a needle. सुई के नोक में से हमारी लाइट जा सकती है. And in Christianity, eye of a needle means your soul should be so pure that you can go to heaven only if your soul can pass through eye of a needle. So such is the tough, as we say for our also, to go to heaven, गाय की पूंछ पकड़ना है, पता नहीं, something like that, तरनी पार करनी है. We should be pure. Similarly, they said the light is so pure, that means almost single wavelength, very intense, and very, very sharp, very small diameter. These are the characteristics of a light which can pass through eye of a needle. They advertise like this. So talking of heaven and Christianity, but the first laser diode they developed was used for air-to-air missiles, for tank, weapon simulations, and all those, for military purpose. And this slowly came into for communication purpose. So laser diodes, what they do? They emit coherent light through stimulated emission, because how the light is produced, how lasers work, is entirely a separate chapter. I will not go into that. But they emit coherent light through stimulated emission. They are mainly used in single mode systems. Because we have to operate lasers, there is a threshold when the lasing starts. In LED, initially actually laser is a LED. Then when the current reaches a threshold, then only it lasers. And we have to modulate light in a very steep curve. So lasers are suitable for digital communication, not for analog. Suitable means they can be used, but they are always used for digital communication. Whereas LED can be used for analog communication also. It can be used for digital also. So they are suitable for single mode fibers because they can pass through eye of a needle. So more light will get connected into optical fiber, single mode fiber. And then the light emission ranges from 5 to 10 degrees cone, so we can connect more with the optical fiber. They require higher and complex driver circuitry. So that is why they are more expensive. And the laser function comes up from three things: photon absorption, spontaneous emission, and stimulated emission. That is how lasers work. As I said, the stimulated emission comes after a threshold. Now imagine if we change the current here and take it to this, it is very, very short time. That is why I said they are more suitable for digital communication. And the lasing threshold is minimum current. That is minimum current we have in this here. Here only laser will. When you give this much current, then only lasing action will take. Otherwise, till that time, what you have is a LED. And when the laser goes bad also, you are able to see a very dim light, which is something like LED. Because otherwise laser you cannot see. It is so bright. Red I am saying. Other one you should not see at all. Or even this you should show any angle. Otherwise you have only one eye after that. So be careful with the lasers. Don't look at them at all. Obliquely, or let it be reflected light from some other surface which you should see. Then laser diodes are also temperature sensitive. What happens is this threshold current increases if this laser is at a higher temperature. As the temperature increases because of the very functioning or very illumination properties, or when you try to increase the current, heating also increases, and this increases the threshold further. So laser can also get damaged because of this. So one more essential thing is that laser should have a constant temperature working, and for that they have thermoelectric coolers and technology to keep the temperature totally constant. I will show you in the chip how they have done, but it requires a constant temperature also, maintenance of temperature. Then only wavelength will not shift, as well as it will not get destroyed, will not get bad. So that is why temperature has to be maintained with the help of Peltier things. Once again, semiconductor laser also has layers of different material which can emit light. And to give you an idea of the layers deposited, you can, sorry, you can see the layers are of the order of 1 micron, 0.1 to 0.3 micron. So imagine how they are deposited that much. But luckily there is a synergistic alliance in here also. We have, semiconductor industry. It's very large scale. VLSI technology is there. So all they have to do is change the materials, because they're also doing depositions through various methods, vapor deposition or etching or whatever. So all that you have to do is you give him different materials. That means you give him different bread and different materials to make a different sandwich. So they could give you these devices also, because they were making photo transistors already. So they started making for you now these photonic devices also. But you can see how much is the layer, 1 micron, less than 1 micron, which is emitting. Now, once again, here also you have edge emitting lasers, a different type of deposition of different materials. The most popular laser diode is VCSEL, vertical cavity. And these vertical cavity lasers, I was going through the literature. On 14th December, just say a week back, Apple has awarded $390 million contract to Finstar to develop these type of lasers for them, which will be used for they are going to use them for use in smartphones, and they will be used in iPhone for cameras and selfies and for many other sensors. So this type of vertical cavity lasers are going to, of course, the intensity will be very low. It will not damage anything, but for controlling such. So this is one of the most popular laser, and this very laser is mostly used for optical fiber communication. This is the other application. So I will also show you a video of this little later, but this is vertical cavity surface emitting lasers, and vertical cavity surface emitting lasers is what I said, most commonly used laser for optical fiber communication. So this is what I said, that they have awarded a 390 million contract to Finstar, and it currently enables what? Face ID, Animoji, portrait mode selfies with iPhone, and true depth camera and other popular Apple features are also being done with this. And now they are going to modify it further so that they can use it for more applications. ये मैम एक बार फिर चला दो मैम. One more video. Otherwise, I used to have a contact from here itself. I don't know why. Okay.
Hello everyone, this is Colin from Fiber Optics for Sale. In this video, I will explain what is VCSEL laser. So let's get started. VCSEL stands for Vertical Cavity Surface Emitting Laser. VCSEL emits light in a cylindrical beam vertically from the surface of a fabricated wafer, and it offers many advantages when compared to conventional edge emitting lasers. Now let's take a comparison between conventional edge emitting laser and VCSEL laser. The left picture shows a conventional edge emitting laser. The right picture shows a VCSEL laser. Conventional edge emitting laser has some disadvantages. The light beam usually has a high divergence angle and is difficult to couple into optical fiber without a corrective lens. Also, it requires higher electrical threshold current to operate. VCSEL lasers have many advantages. It has a circular light beam, which is very easy for coupling into optical fibers. It also consumes less power. Since it emits from the surface, this structure can be integrated in two-dimensional array configuration. Now let's see how VCSEL lasers work. A VCSEL laser is typically composed of several layers. The top layer is the electrical contact for current injection. The next layer is the high reflectivity top mirror, which has a 99% reflectivity. This layer is made of DBR, which stands for Distributed Bragg Reflector. Then the next layer is an oxide layer, which constructs a light emitting window, so the light beam can be optimized into a circular beam. The center layer is a laser cavity. It is usually a multiple quantum well layer. This is an active gain region where lasing actually happens. We will talk about quantum well in the next slide. Then another oxide layer to confine the light. Last is the bottom DBR layer, the bottom mirror, which has 99.9% reflectivity. Notice that this reflectivity is much higher than the top mirror, so that lasing light will get up from the top mirror instead of the bottom. The right picture shows how the lasing really happens. The quantum wells generate photons which get bounced back and forth between the top DBR mirror and the bottom DBR mirror. This is a typical lasing mechanism as in all lasers. The active region in a VCSEL laser is usually a quantum well structure. This slide shows the basic structure of a single quantum well. This structure can be repeated several times to construct a multiple quantum well. A quantum well structure is made of 3 layers. The 2 aluminum gallium arsenide layers are thick, and in between is a very thin gallium arsenide layer. In fact, the central gallium arsenide layer is so thin that electrons cannot move freely in the vertical z direction, but only in the xy plane. This is called quantum confinement. The quantum confinement effect increases the lasing efficiency, which is a big advantage over conventional double heterostructure lasers. The aluminum gallium arsenide layers have a wider energy band gap, as shown in the right picture. The gallium arsenide layer has a narrower energy band gap. This is called a potential well, where the quantum well name comes from. The theory of how quantum well works is much complicated. We cannot cover it here in a short video, but you can research this by yourself in order to fully understand quantum well lasers. VCSELs have high performance and low cost advantage. The key features are the structure can be integrated in 2-dimensional array configuration. Low threshold currents enable high density arrays. Surface normal emission and nearly identical to the photodetector geometry give easy alignment and packaging. Circular and low divergence optical beams eliminate the need for corrective optics. Passive versus active fiber alignment combined with high fiber coupling efficiency. Low cost potential because devices are completed and tested at the wafer level. Lower temperature sensitivity compared to edge emitting laser diodes. High transmission speed with low power consumption. So there you have it. Please.
So as I said that this is the most popular laser for optical fiber communication. It also has a fiber coupling. So in order to avoid coupling light into optical fiber, we already in the factory itself many times an optical fiber is pigtailed, sealed and frozen with the laser in the receptacle or in the housing, and then all we have to do is connect now fiber to another fiber, for which there are so many facilities, and even in the lab you will be doing that. So coupling of fiber is there, and in order to select a particular wavelength, because after all, even if laser we say is a coherent, still it has got a many other wavelengths also, very near, maybe very near. So in order to focus only one particular eye, there has to be some kind of an arrangement, either a prism or a grating. So we have a Bragg grating at behind, so that it reflects only one wavelength and we can get pure light of now 0.1 nanometer or 0.2 nanometer here and there. So we can also get light of a single, almost single wavelength. For that also, these things are maybe external to the chip or can be inbuilt in the chip also. So there is a possibility of tuning the wavelength also. So you can tune the wavelength just like you can select with the help of a grating. Different gratings, if you use, different light will be reflected. So you can also tune them for a single frequency, which we will be needing much more when I talk about wavelength division multiplexing tomorrow, because we are sending many wavelengths together. We have to combine them and then separate them. And the nearer they are, more we can pack. So more will be the bandwidth of the total system. So this tunability of laser is very important for wavelength division multiplexing and dense wavelength division multiplexing. I will not go into it. Edge emitting, and then you have outside tuning, and then you have inside. This we can from inside itself we can reflect only a particular wavelength for this. These are some of the technologies used for that. Now, if we compare the sources broadly, I will say LEDs can be used for digital as well as analog modulation, but they can be used only with multimode fibers. Whereas laser diodes are more suitable for digital communication, but they have a temperature maintenance problem which has to be taken care of, and which is taken care by the designers of the receptacles or the light source module itself. They make sure that the temperature is maintained with Peltier elements. This is a laser diode transmitter. So what you have actually possible, you have, you know, a chip itself. It is not only a single transistor like thing. You have a transmitter which has got a cooling system, which has got the electronics to condition your signal into 0, 1 or to the level that you want to give it. So electronics before the source, and then maintenance of the source, maintaining the temperature very precisely. If over a period of time the intensity goes down, all light sources, intensity goes down over a period of time. If you have your LED bulb, or even if you have your tube light or even tungsten lamp, over a period of time the intensity goes down. Similarly, in case of lasers or LEDs also, it goes down. But we know that if we increase the current, then once again the illumination will be received. So we have a photodiode which senses the light, and if it goes down, it increases the current. So that also is inbuilt into this very module. So now we have, actually, as a user, you don't have to bother for how it is made or how it will maintain itself. So you can see, now all you get, Finstar, this company, it has a module. This is almost a transmitter for you. You just have to feed your signal, the red arrow, and it will convert it into light modulations, and then you have to connect your fiber to another fiber through that. This will be the connector to connect to your spool or drum, which may be hundreds of kilometers. So, but the heart of this is light source, and that is laser. So even a person who is trained in a diploma holder or a degree in electrical or electronics, he can very easily combine things. Just give the proper voltage to 5 volts and then everything will work. So transmitters are also packaged. Now we have less time. So the other part we should not forget. You have launched light, fine. But then you should be able to recreate the signal that you sent. And imagine the signal which is reaching the other end can be picowatts. Pico. What you sent was a milliwatt. If for a bad device, microwatts. But what could be detected nowadays is even picowatt can be detected. So you will increase the distance in such a way that your detector is sensitive enough to do that. Like if I start shining a light at night even, then how far you will be able to see. And if I increase the intensity of that, you will be able to see farther. So same is the case in this case. How long fiber I can have with the light emitted so that I can detect also. So detectors are also equally important. Now, again, the requirements of an optical detector are it should be highly sensitive to operating wavelength. To that particular wavelength, it should be very, very sensitive. Then it should have high fidelity. That means on and off. It should be able to discern. Supposing I will not discern, on and off of more than 14 per second. That's how the movies are possible. The cinema is possible because of persistence of vision. But my detector should not have persistence of vision of that order which our eye has. It should be able to discern in giga, megabits also. Mega times, the on and off takes place in digital system. It should be, it is 0, it is 1, it is 0, it is 1 in millions of times. So it should not have that persistence of vision. And it should be having a very large electrical response. That is, for a very small signal also, I should get sizable signal, which I should be able to amplify. So it should be sizable signal. That is sizable in the sense, it should be much more than the noise. Much more. Then only I will be able to separate the information. Then short response time. That means that I already said persistence of, it should not be that. Minimum noise introduced by itself. The detector, they have a property called dark current. Even if there is no signal, some current is there. Some people, see things, even even if they are not there. I tell you, light hai, nahi hai, nahi hai. But after some time, hai, वैसे ही बोल देगा. So it should not be like that. So it should not have noise of its own. So dark current, it should be definitely stable. It should be very stable. It should be small size. It should have a low bias voltage. And it should have high reliability. It should have low cost. How is low cost possible if you want everything? So cost will have to be compatible with the features that you want. You cannot have all those things and still low cost. So these are the requirements on optical detector. The cost you will have to do, optimally what you want, and on that the cost will depend. Then LED, as I said, is the base. That reverse bias the LED and it becomes a detector. So they could work very fast, because before that they had photo cells, they had photo tubes, they had photovoltaic cells, with which you could detect light. Photo transistors then came up, and then for requirement of communication, they had to develop special detectors. But once again, the starting point was the PN junction. And now a reverse biased PN junction acts as a detector. So when the light falls on the junction, then electron and hole pairs, they combine, and you will have a current, and that current is our detection. But we also want that this bias voltage should be low. So आप 5 वोल्ट रखना चाहेंगे, 5 से ज़्यादा नहीं रखना चाहिए. Initially we were biasing with something like 30 volts. Some of the detectors that we got in the beginning. So you have a different battery for bias. Then only you will be able to detect. For APD, I remember we used to bias with the photo multiplied power supply, which goes to 900 volts. So biasing is important, and bias should be from a low voltage. So that is also one requirement. Now, the input-output characteristics of a diode are that as the light intensity, more light intensity falls on that junction, more current will be produced, more current will flow. And I said, the detectors are of the order of picowatts. So imagine how efficient that junction has to be for this purpose. Initially, the PN junction was used, but they found a lot of limitations with that. So what they Then they experimented with it, just like in kitchen, you add few things, masala. And then similarly, these engineers, group 3, group 5, they keep on, those are the dopants and the impurities. And what you have is semiconductor, group 4. So if you change the flavors by giving different materials, different concentrations, different layers, and you come out with new things. Group 3, 5, 4. 4 is semiconductor, 3 and 5 dopants, and impurities, phosphorus or whatever. So they needed this, and it has a narrow depletion region. There is a need to increase the width of the depletion region without manipulating unnecessarily value of reverse bias. So they have come out with something called pin configuration. Pin. I stands for intrinsic. And very thin layer of intrinsic material has improved this intrinsic P and N. So this has improved the detector, and now it is possible to detect that picowatts also. So this is the change which they did to PN junction, reverse bias of course, to get detector for the communication applications. Here is another way of showing that top layer will be metallization, below also will be metallization, in between you have P, I and N. The advantages is that intrinsic layer is thick, so more number of incident photons enter into this layer and generate electron hole pair. So result of high quantum efficiency of the device is there. Reverse bias is small, usually 50, because the thickness of the depletion region is controlled by the thickness of the intrinsic layer, not by reverse voltage. And it has a high bandwidth, as I said, 110 gigahertz is possible with pin photodiodes. They have solved our problem of high data rates. The wavelength response materials are silicon can give you 400 to 1100 nanometers. 400 is what? Blue. And 1100 is ultraviolet. Do you think it will be useful for fiber? You are working at 1300 or 1550. So silicon detectors are not of much use to us. Of course, they were okay for the first window, 910 and 800 to 900, they were useful. Then germanium can respond to 800 to 1600 nanometers. But germanium also I found it is temperature sensitive. So germanium is not a very suitable material for detectors. Then comes the gallium arsenide. It gives you once again 400 to 1700 nanometer, or even better 1100 to 1600 nanometers is Indian gallium arsenide phosphorus. So the pin detectors are now basically Indian gallium arsenide or Indian gallium arsenide phosphorus. These are the materials used for fabricating or manufacturing or producing detectors for communication applications. And you will have, there are the specifications that you have available with the device. They will give you which region your what is the region where your device will be having maximum responsibility. But in between also you can use it. In between wavelengths also you can use it. That's not a problem, unless it is at the lowest or the one which is lowest. Then on this curve, you can use it wherever is your the 1.3, 1300 nanometers also you can use it. For 1500 it will be more sensitive, but even for other wavelengths 1100 also you can use this particular. So this gives you one thing, how efficient your device will be at that wavelength. That is one thing. Then there are times, when the optical fiber is passing through a region where you cannot have a repeater, or your signal has depleted to even less than picowatt. Then earlier we used to have a photo multiplier tube, in which there were number of diodes, and each time one electron will generate, or it will produce 10. These 10, when they go to the next diode, which is at a higher potential, this was in a tube version, valve version, then those 10 will generate, each will generate 10, so it will multiply by 10. So 40 multiplier system used to, but this, as I said, this needed something like 900 volts, because each diode has to have different voltage of 100 volts each. So they said, when we can do this, can't we do this in solid state? So they have come out with detectors. So they have come up with avalanche photodiode, which is also P, I, P, and N. They have added a layer into this, and now this is able to give us avalanche. So even less than picowatt, you can also detect. So for the time being, at that place you generate that much, and at the nearest you can once again amplify your signal. So avalanche photodiodes are very low light, can be, even they are used for other applications also. So in starlight you can see everything, even in a very dark night, just with the light of the stars you can see the intruder, or you can see any area, or monitor certain other parameters. So avalanche photodiodes, this you should remember that the detectors are, first were PN type, then pin, and then another type of detector is avalanche, but you will hardly come across it in the communication systems as such. So this is APD, and high resistivity p-doped layer increases the electric field across the absorbing region, and high energy electron hole pair ionize each other sides to multiply the current and leads to greater sensitivity. This is the mechanism. Now comes, as I said, the photodiode should not generate its own noise. With somebody, a child, he will not sit quiet. Same is the case with detectors also. They have inherently, they have some noise, because you, at the same time, you want it to be sensitive enough, and you don't want that it should have its own noise. It's very difficult. So it can be due to short noise. Nothing is happening, just one electron will shoot on its own, and that can give you some kind of a signal type of thing. So you will have to control that. It is known as short noise. Then thermal noise. After all, you are not able to maintain temperature very, very exclusively. So due to variation in temperature also, electrons can come out, which are not due to signal. So that this is what is called, second thermal noise is called Johnson noise. And these are the mechanisms for those lights. I'm not discussing that. Dark current noise, when there is no signal falling on the detector, then also some noise is there, and that is dark current noise. This is there even in any photo detector. Dark current noise is there in any whether it is photocell, whether it is phototube, whether it is what I said, photo multiplier tube, there will be dark current noise in any. So you have to take care of that. And excess noise even in pin is due to avalanche multiplication process also. Sometimes there is noise. So what for we have studied the detector. Ultimately, you want to make a receiver. The light which is coming from the optical fiber, maybe it was modulated for sending you the encyclopedia, or maybe it was from a TV channel, a TV program, or data. You want to convert it once again back to that information. Once again, just like we have now transmitters built in, I showed you small Finstar transmitter. Same way, you at the other end, you want to build a receiver. So receiver will not have only detector. The signal that you get from detector, you will have to make it into, light signal will have to be converted into electronic signal. So you have all the electronics preamplifiers, amplifier to correct the sync. So you have some Schmidt trigger or those that digital electronics you will need to convert that signal, if it is digital, back to what you sent. And you will also compare what I sent. Did I get that? Were some bits missing, or whatever typographical error is okay. But if there was no error, still you have some kind of a typographical type of error, or you have a message which is totally different from what you sent A, it took something else. So all those things have to be taken care. So you design a receiver. So receivers are possible, which are just of the size of a matchbox. Initially they were like tiffin box. Now they are matchbox, and even smaller than matchbox, just like pen drive, size of pen drive, in which you are just connecting the optical fiber. There it was pigtail. Here it is not a pigtail. It is into a connector. Most of the time, of course, people have made something like pigtail also, but that is only connector. Detectors are not connected pigtail as such. Connector may be having another fiber so that you can connect fiber to it. So you have receivers, 3 gigabit or 100 gigabit, and they have taken care of all the electronics. In the, supposing we see this, in this it is a voltage you are giving, then you are getting the signal, and for monitoring purpose also outputs are available at different levels of the amplifier, play amplifier, or synchronizing. So this is the types of it. So this is the functional block diagram of a receiver. The fiber is coupled to this. Sorry. So it is falling on pin photodiode, then a preamplifier, then you have filters, amplifier limiters, decision circuits, all this, and ultimately signal you get, data and clock also you get. You can synchronize with other things. As I said, you will have to check the bit error rate. So what we do is, with the communication system we keep in the lab, and we generate pseudo random bit sequence, PRBS. It's like equipment is there, and after passing through this, we check, and we are also passing the signal directly to the other equipment, the receiver side, and we compare the two. So if there is bit error rate, or bit error rate cannot be found otherwise also, but bit error rate equipment is there, and what we sent, are we getting that? And we keep on increasing the data rate. So that we can check the receiver and also the transmitter in the lab, and then only we install. So, and in the installed system also we can do, probably we are going to have some thing on bit error rate also. Bit error rate can also be checked with a eye diagram type, say with oscilloscope. So that this is also, there is also a methodology to do that if somebody does not have that equipment of bit error rate system. So with this I will try to say that Cow also said one thing. We started with Cow. Cow said during his Nobel laureate lecture that he was asked, can fiber optic systems be replaced by something else in the times to come? Because you are now having terabits. He said, I will say no. But when I was working on waveguides and I said optical fiber can be used for communication, many people said no. It is not possible. I also agree with them. So something better, something else can come.